And in this part, so first of all, this is joint work with Ido Bentov, who's now at Cornell doing a postdoc with Elaine Shi. Inon Choresh, who's a master's student at Technion, and Michael Ryabtsev, who's doing a PhD with me. He's somewhere around. Oh, he's all the way at the back. Okay. And this is a paper that appears as of last week on ECCC. I'll give pointers here, but I hope this is sort of a teaser and encouragement to read it, okay? And again, I won't go deeply into the math, but I'll sort of give an idea of what goes on. So the previous talk sort of set things up for this. We're going to talk about the Reed-Solomon proximity testing problem, and then we're going to present a new protocol for it that has a rather long name, so it's compressed into FRI. I will say the name later on, but it's kind of long. And I want to sort of expose the similarity between FRI and IFFT. So the F in FRI is fast, and the first F in F is fast. Sorry, the first F in the IFFT is fast. It's the fast Fourier Transform. And there's a similarity, and I would like to try and expose this similarity. Good. So that's the plan. So FRI solves the low-degree testing problem. And this is a problem that has many, many solutions, and they all appear in things like PCPs and so on. They do not appear in these cryptographic systems that sort of, again, circumvent it. So now we're in sort of a, let's call it transparent land. So transparent systems, I think, invariably should face problems like this. Many of them do. So there's no trusted setup. Let's assume there is a function. It could be the same function from the last example. So it's evaluated over a huge domain, like a billion. And the queries to F are costly because, and this is the real reason, they are going to be a major part of a Stark proof. Or in the Ligero system, a Ligero proof. Or in a Zikabu system, a Zikabu proof. OK, so we want to minimize that number of queries. And the problem we want to solve is to decide, with a minimal number of queries, whether F is good. It has degree less than 1,000, so I sort of lowered the degree now. It was 1,000,000, now it's 1,000, but it's the same thing. Or F is bad, meaning its degree is greater than 1,000. And I'll ask a question that appeared up previously. How many queries do you think you need in order to solve this problem?
3.
How? No, in this model, all you have is F. You have a lookup table F, and you would like to know whether F is of degree less than 1,000 or degree more than 1,000. So you're willing to accept any table that's a polynomial of degree less than 1,000, but you want to reject all tables that are not, whose polynomial expression is degree greater than 1,000. So you can't do it with 3. It's easy to do it if you read the whole table. But it's actually impossible to do it with less than 1,000 queries. Actually, the way it's stated, it's even impossible to do it with less than reading all of the table, because the very last entry you didn't read could be not part of that low-degree polynomial. So it's sort of the same problem as before. But don't worry, we're going to make progress, okay? So, and again, just the focus previously was on how you would use low-degree polynomials to express statements about computation. This is a different topic, but it's related. It is about, now we forgot about computation, or rather, we reduced the problem of computational integrity to a very clean algebraic one that doesn't care about computation. It only asks to distinguish between tables that are polynomials of low degree and things that are not. And the previous talk sort of motivated why this could be useful. Okay, so just reading less than everything doesn't help us solve the problem in this model. So let's simplify things for the verifier. What if we we allow a little bit of slackness? So we're going to say F is good if it is a God-honest evaluation of a low-degree polynomial. But F will be called bad only if it's really, really bad. So one entry, not agreeing with a low degree, sort of okay. It's a little bit of noise. It could happen. 10% of its entries must be changed in order to make it a low-degree polynomial. That's bad. Only then is it bad. So now things are a little bit simpler for the verifier, for Alice to test, right? Because, I mean, there's more like, only if there's an extreme level of noise should Alice reject. So now can we solve the problem with a small number of queries? So again, we can read everything, but it's impossible to do even with less than 1,000 queries. And again, if we didn't allow any randomness yet, so whatever queries Alice is making, Bob could put all the errors somewhere else. And again, we're in this situation where you need to read pretty much everything in order to solve it. For instance, it's on, you know, on almost everywhere it's 0, but for a negligible fraction, but it sort of is hidden somewhere. So you need to read everything in order to find this negligible fraction. So let's make things even simpler and allow Alice to randomly sample entries inside F in the lookup table. And now we want to do it, and we're even going to allow an error in our process. So all she needs to do is the following. If F is a low-degree polynomial, she needs to always accept. If F is very far from being a low-degree polynomial, she needs to reject with probability half, but it's okay for her to have some error. So what do you think? Let's do it with lines. Suppose we want to know whether something is a line, strictly a line, or we want to reject any lookup table that is not close to being a line, that you need to change at least 10% of its entries in order for it to agree with a line. And the hint is that you can find the slope and the intersection of a line from reading any 2 points. So that's the hint. So any suggestion how to solve the problem more efficiently? What? You read, for a line, you would read 3 points, 3 random points. You would take 2 of them and say, oh, let's suppose let me get the slope and intersection point from the first 2, and let's see if the third one matches up with what should happen. And of course, this has perfect completeness. If everything is on a line, this test passes. And if 10% are far, then one can show that you will actually reject with probability at least 10%. So now, if you increase the degree, you need at least degree many points in order to interpolate what the line or parabola or whatever the degree d thing is. So you can't do it with less than 1,000 points, with less than d. But here's a theorem by Rubenfeld and Sudan from 1995 about testing, low-degree testing, that shows that you can do it with exactly degree plus 1 entries. And this is a really tight result, because you can't do it with d entries, and you can do it very well with d plus 1 entries. The proof of this theorem isn't very difficult, but of course that paper has a lot of extensions and is a very influential one. Okay, so now we have a number of queries. We can solve the problem with a number of queries that is equal to the degree. But the problem is that the way we got F was from execution trace, from some execution trace of a very long problem, of a very long execution. So if we're going to read degree many points, it's exactly like reading the whole execution trace. And that's not a good idea. We would like to read much less queries than the whole execution trace. So we would like to solve this problem with a number of queries that is much smaller than the degree. But the problem is that it's impossible. We have an impossibility result, a mathematical impossibility result. So the suggestion that goes back a very long time ago to the early days of probabilistically checkable proofs and interactive proofs and things like that was to ask Bob, the prover, to add to F some additional information that would make life easier for the verifier. And this thing is known as a proof of proximity, or, yeah. So now we're in a different game. Alice, just like before, Alice told Bob, listen, I need this auxiliary G. Now for solving the problem of low-degree testing, Alice is telling Bob, listen, F is not enough for me. You need to give me something else that's called pi. Pi is a proof. Give me a little bit more information, but we want to play the same game as before. If F is low degree, there exists some pi that will be verified to be okay. And if F is not low degree, then for any pi that Bob tries to cook up, Alice will find that something's wrong. So our new algorithm, Fry, actually solves the low-degree testing problem in this setting, that we assume that Bob has written down not just the function f, but also some auxiliary information. And by the way, everything I'm discussing in both of these lectures is about transparent systems. So he actually writes down these entries, and then he commits to them using, let's say, a Merkle tree. And later on, he's going to open some entries up. But there's no cryptography in the part that I'm describing here. The cryptography only comes in order to enforce commitments and proofs that revealed entries agree with what was committed to. So that's the only cryptography, and it sort of comes in a different place. So we're in transparent land. So we would like some system for Alice and Bob to interact such that Alice will accept good low-degree functions with the proper information, but reject things that are far. And we already saw previously that you can do it without any extra information, but with number of queries that is at least the degree. And the way I actually got into the moon math part of, the theoretical part of looking at proofs was, again, around 2003. This is one of my results from that time, that you can actually do it in this model with an auxiliary proof. And the auxiliary proof is actually not too long. So if f was length t, this thing becomes t times log t to some power. So it's scalable on the prover side. On the verifier side, the number of queries becomes logarithmic in the degree, which is great. But there's this exponent. So everything you take logarithm of d, but you need to raise it to a power c. And this c is roughly 3. So log, in our setting, where the degree and the objects are 1 billion, so log of 1 billion is roughly 30, and 30 cubed is already 27,000 entries. So the query complexity turns out to be more than what you could do without a proof. So what we're facing here is the problem of concreteness. So we have a lot of great asymptotic results, but they start kicking in only for very large values. And a lot of my research has been about looking in the concrete world, like what is the smallest size instance for which you actually get some savings that is predicted asymptotically, but can you get it also for things in the here and now? So I described what the Reed-Solomon proximity problem is. Now I want to tell you about what Fry achieves first. So assume you have this function f. I think s was 1 billion. Now it turned out to be 1 million. OK, well, maybe there's a minor inconsistency. But it's a huge table. And here's how the protocol is going to work in Fry. So it's what's called an interactive oracle proof of proximity. So Bob, first of all, posts f. Now, after he posted f, or committed to it, Alice tosses coins and sends some randomness. But this randomness is public randomness. There's no secrets in it. So she could just watch a randomness beacon and use that. Or she could use the, some hash from blockchain and say, these are my queries. And now Bob, depending on this first piece of randomness, commits to another part of the proof. And this repeats. The verifier sends more public randomness. And there's another part of the proof. And this goes on for a while, and then it terminates. And only after all this process of sending randomness and committing to stuff, only now does Alice go and query everything that was committed. And again, when she queries, she uses public randomness to pick the queries. So the whole use of randomness from Alice's side is completely transparent. She just needs randomness to send to Bob, and then she just needs randomness, public randomness, to pick the queries. So this is an interactive oracle proof of proximity, which is something that we've been studying recently with Alessandro Chiesa and Ariel Gabizon and Madar Zvirza, the T should be a V here, and also with Nick Spooner, Michael Ryabtsev, Bakhtiyar Ryabtsev, and yeah, it's an exciting topic. So here's the theorem that we get in Fry, and again, there's a paper posted online that I hope this will encourage some of you to look up, and this is the theorem stated there. So if you have a degree D testing problem, and the domain size is n, then actually the total proof length, so the sum of all lengths of all proofs that the prover generates, is less than n over 3. And the prover complexity, the number of arithmetic operations the prover overall uses, is less than 6 times n. So 6 times n arithmetic operations. Some of them are additions. I mean, usually multiplications cost. And by the way, it's like fully parallelizable, so it's in logarithmic time. So it's very hardware acceleratable. The query complexity is 2 times the logarithm of d, and the verifier complexity, the number of arithmetic operations, is at most 21 times log d. Now notice, I mean, usually theoreticians, they like to write O notations and hide things in exponents. So there are no things hidden by exponents here. Sorry, no asymptotic notation. These are the numbers. And the round complexity, the number of interactions, is half of log d. And what you get in terms of soundness is f is delta far, where delta is some number between 0 and 1, let's say 10%, then you will reject it with probability at least delta. So for instance, if you have this table with 1 billion entries and your degree is 1,000, so in the Reed-Solomon setting, you could do it with roughly 1,000 queries. In my work with Madhusudan, you could do it with 27,000. Again, it starts kicking in for larger values, but for this setting, for this concrete setting, you wouldn't get any savings. And with the new system, it's 80 queries. And actually, 80 queries, you need 20 queries in order to get rejection probability of 10%, and you repeat it 4 times to get to boost the rejection probability to more than half, for the error to less than half. Okay. And this has no cryptographic assumption. So this is a proven mathematical theorem, assuming we don't have bugs. Okay. So I described what Frye achieves, and I just want to say that, I mean, as far as efficiency goes, in terms of prover complexity and verifier complexity, I think there's not a lot of room to, save. The main thing that would be interesting to focus on is on the round complexity. Would be interesting to get the number of rounds down, even though practically speaking, you could apply the Fiat-Shamir heuristic and basically make it all non-interactive. You can't analyze this theoretically, but practically worse things have been known to be used. So, but it's a great theoretical question whether you can achieve the same things with round complexity that's smaller. So the last part, I want to explain why it is similar to the fast Fourier transform. And for that, I want to, okay, anyone who knows or what the fast Fourier transform does, please raise their hand. Good. All of those who remember the recursive algorithm also raise their hand? Okay, good. So you had good teachers that, or you maybe are actively working in signal processing. So the fast Fourier transform is really important, and it really rocks. It's used in signal processing, fast integer multiplication. It's used in things that are not yet implemented, things like factoring. When we speak on the phone or take pictures or videos, there are FFTs, backwards and forwards. Yes?
Why do you use IFFTs and not things like DFTs or wavelets?
So FFT and DFT are the same thing for me. And wavelet, you'll see the analogy to the FFT. I don't see an analogy to the wavelet transform, but who knows? So the FFT and DFT, I think I treat them as the same. Okay, so the FFT solves the following problem. It's the multi-point evaluation problem, which says you're given a formal sum that's a polynomial, and you're given a range of evaluation. So please go from the polynomial p to the function f. That's what it solves. But it does it very quickly. That's why it's the fast Fourier transform. And the inverse Fourier transform, the IFFT, goes the opposite way. So you're given a table, and you're asked to interpolate and find the polynomial, and that's what the IFFT does. Okay. Now often in signal processing, it's about time and frequency domains, but really, it's mathematically, this is what happens in the FFT. And you can define the Fourier transform for any evaluation set, but it becomes fast only for very nice sets. And usually when you learn the nice, like when you study it, especially in signal processing or in a computer science class, you will see it. The nice set will be the roots of unity of order 2 to the n, usually the complex roots of unity of order 2 to the n. And what you actually, the only thing you need is you need S to be a group of order 2 to the n. So, and we'll use such nice sets that are IFFT friendly. Okay. So let's just describe a little bit the inverse Fourier transform attributed to Cooley and Tukey from '65, but also attributed to, I mean, Gauss knew everything, so he also knew this, apparently. But, you know, he got enough credit, so. So, no, I mean, the application to engineering, who knows, maybe he also saw that, but, okay. So, now, it's called the fast Fourier transform because it solves it in quasi-linear time. So for domains of size n, it runs in time O of n log n. Good. And here's what it does. The IFFT, or the FFT, it's the same thing. You spend linear time, so O of n time, and after you spent that time, you broke the problem into 2 identical subproblems of half the size. And now you can solve them separately, independently. So you recurse on both problems. And it's not hard to see that after log n steps, you know, you went from n to n over 2, n over 4. And after log n steps, you're at constant size. And then you can solve the problem easily, like 2 points, getting the line. Good. So the recursion depth is log n, and each level costs you theta of n steps. So you get total running time n log n, quasi-linear time. And that's the fast Fourier transform. So Frey solves the fast Reed-Solomon interactive oracle proof of proximity, solves a similar problem, not the same problem. I mean, I wish we had a faster Fourier transform, because this is going to be faster, but it's not going to solve the Fourier transform problem, but it is very similar. So our problem is to prove interactively that the degree is less than something, let's say size of the domain over 8. And again, Frey solves this faster than what the FFT's running time is, but again, it's apples to oranges. It's a different problem. But it's still, I think this qualifies as fast. So what you do is you spend linear time to reduce the problem to a single problem of size n over 2. Not 2 problems, 1. And then you recurse. But now you're recursing on a single problem, and what you get is this geometric sum. So it's still log n layers, but it's like 1 plus half plus quarter, blah, blah, blah. And that thing turns out to be theta of n. Okay. So as I said, it's faster than the FFT, but it's not a fair comparison because they solve 2 different problems. But the more important similarity is in how it works, because it's very much like the FFT. And this is the last part that I want to explain. So what I'm going to do is I'm first going to recall the fast Fourier transform, and I'll probably recall it in a way that it's not the usual way that you see, but it's the way that will show the similarity with Frey. So we need S to be this nice set. So the nicest of sets, the ones that is used when the FFT is taught, and when I teach it in my classes, you would take omega, a root of unity of order n. It could be a complex root of unity, and n is actually a power of 2. And then you define the set S to be all the powers of omega. So, and it cycles around. So, like, I mean, for instance, if it would have been order 4, the omega would have been I, and then this set S would have been 1, I, minus 1, minus I, and then it circles around. Okay. And now we're given F that's an evaluation, and we would like to find the interpolant. And it's evaluated over this weird set. So what the way the inverse FFT breaks the problem into two subproblems uses the following observation. If instead of taking omega, you take omega squared and look at all its powers, you would get a set of half the size. Actually, you would get a subgroup of half the size. For instance, if instead of taking I, which gives you 1I minus 1 minus I, if you would take I squared, what is I squared? Minus 1. So the group would have been minus 1, 1. right? So if you take the square of omega, you get a group that is half the size. And this is a general phenomenon. So if you would have worked, for some reason, with omega squared, you would have got a group that is exactly of the same structure, but just half the size. Cool. And here's another observation. You can take any polynomial and decide to take the even powers and the odd powers and write them separately. So you could take all the even powers, x squared, x to the 4, x to the 6, take their sum, put them on one side, call that thing p0 of x squared. And then you could have all the odd exponents, x, x to the 3, x to the 5, and so on, and write them on the other side, call it p1. And it's not hard to see that you would get this equality, that p of x is the even exponents with x squared plus x times the odd exponents. So this is another observation that is true of any polynomial. And what the IFFT does is it is going to compute f naught, that is an evaluation of p0 on s prime, and f1, that is an evaluation of s prime, on s prime of p1. And if you did that, you could, if you did that, you will have gotten, you started with a problem, you had f, you wanted to find p. But you know that p is really just p is a sequence of coefficients. So you're going to say, well, I'm going to make this into two problems. I'm going to find the even coefficients, that's p0, and I'm going to find the odd coefficients. So the way the IFFT does this is it says, I'm going to get a function f0 that from it I can deduce all the even coefficients, and I'm going to get the function f1 that from it I'm going to get all the odd coefficients, and now I have two separate problems, which is exactly what we wanted. And this is how you get these two, how you separate the big problem into two subproblems. So you define this bivariate polynomial. So we just sort of plugged, instead of x squared, we plugged a y. And we notice that if we plug x squared back into Q, you get p of x. So if I just sort of, it's just a naming thing. Instead of using x squared inside p0 and p0, I call it y. But I know that, and now I get this bivariate polynomial, but I know that if I would plug into y the value x squared, I'm back at p of x. So this is just some algebraic trick. But the nice observation is that if I want to know, okay, if I plug into the polynomial q, if I plug into it the value, if I plug into x the value 0, what do I get? If I plug into x the value 0, I get here 0, and I'm left with only p0, which is really what I want. These are the even coefficients. So if we could find the values of q, x, y when we plug in the value 0 to x, we will have the function needed to find p0. And similarly, if we will plug in, once we did that, if we will also plug into q the value, into x the value 1, we could retrieve from that p1. So it turns out that all we need to do is to compute this bivariate polynomial q at the points 0 and 1 for every y0 that belongs to the smaller group. And now the observation is that if we plug in y0, we get a degree 1 function, or a line. And if we want to find the coefficients of a line, we only need 2 points. So any 2 points on which we can evaluate for a fixed value of y0, we could find the line and get the things we need. And there turns out to be 2 roots that you can do, that you can find. Now, I'm pretty sure I've lost almost all of you, but the slides will be online and you can study them later on, because the reason is that this is really what happens with Fry. So all we used is that the inverse FFT partitioned our domain into pairs in some way and used each pair to compute some line. And from that line, you could evaluate the new function that you needed. And really, Fry, what it does, it starts off the same way, but then it samples a random X nod and sends it to the prover. That's its randomness. And the prover sends the evaluation of the bivariate polynomial Q on this new line. That's a random combination of the two FFT parts. And then you recurse on this problem that has half the size. So I'm going to sum up a little bit early. So in the paper, we provide a new solution to the Reed-Solomon proximity problem. You have multiple rounds of interaction in the interactive oracle proof of proximity model. But again, if you use the Fiat-Shamir heuristic, so practically speaking, you're probably fine with compressing them all into some non-interactive thing that we don't know to break and don't know to analyze. This is the first solution. Now I'm saying some theory stuff. It's the first solution for a proximity problem that has strictly linear arithmetic complexity on the prover side with any kind of sublinear query complexity for the verifier side. And it also has strictly logarithmic verifier complexity and query complexity. So it has very good, constants in all parts involved. And it's concretely efficient even for very small input lengths. And what I didn't cover is why is this sound, right? So I didn't tell you why is this sound. The completeness is usually not too hard. And here's, if you want to take, or if you remember, this is the place where you should go and download the paper and read it. And if you find anything that's not clear, please write to us. So just summing up, it's something that looks very much like the FFT. Running time is faster than the FFT. It is a major component in Stark, and it gives you very efficient, concretely and asymptotically, very efficient proximity testing protocols for low-degree polynomials. So thank you very much.